This is section 5.7, Inverse Trigonometric Functions, Differentiation. So, first statement I want to make here is none of the 6 basic trigonometric functions has an inverse function. This is because, of course, none of them are one-to-one, and a function must be one-to-one in order to have an inverse. So let's talk about what you would do. I may do, I think, 3 of these and have that suffice for all of them because they'll end up having kind of a similar thing. I'm going to go through this rather rapidly because of the fact that you should have seen this in pre-calculus. All right. So if we were to graph y equals sine of x, there's some things that we know about it. Sine of 0, of course, is 0. Sine of pi over 2 is 1. So middle, high, middle, low, middle. They're going this way, low, middle. And when you graph this, of course, it's not one-to-one because it doesn't pass the horizontal line test. In other words, for each y, there's not just a single x. For example, for y equals -1, there are obviously at least 2 answers, and because the graph goes on forever, infinitely many times, will you hit a y value of -1. So it's not one-to-one. And so there are 3 rules about how to restrict the domain of a function to make it one-to-one. Those rules are: 1, keep the entire range of the original function. So if you look at that graph, its range is from -1 to 1. So I can't, for example, I can't just have my restriction cover only 0 to 1. It has to have every y value represented in it. Okay? 2. If the function's periodic, stay as close to 0 as you can with your restriction. Okay. So, although there are a lot of choices, you could, for example, decide to keep from pi over 2 to 3 pi over 2, and that has every y value from -1 to 1 in it. And what am I saying? I started writing the wrong thing. Pi over 2 to 3 pi over 2. And that would make number 1 true. We keep the entire range. But is there another interval that's even closer to 0? Well, how about -pi over 2 to pi over 2? Can't get any closer to 0 than having 0 as part of your interval. And in fact, that's the one that we're going to keep right there. That's the closest to 0 we can get. And so I'm going to color the part we're keeping in red. And so with that domain restriction, saying we're going to make our domain be -pi over 2 to pi over 2, that function in red is now one-to-one and invertible. The third restriction, which we didn't actually need this time for when you're trying to restrict the domain to make the function one-to-one, is given equally good choices, one using positive x values, and the other using negative x values. Oh, I forgot to write positive. I said it but didn't write it. Using negative x values. Choose positive x's. Which wasn't an issue this time. So that's why I didn't really worry about it, except for I did want to say it. It will actually be a thing we have to think about for cosine. We'll see that in just a minute. Okay, so the thing that happens when you write an inverse function, that if you write the inverse of it, you rewrite it so that every y is an x and every x is a y. You're interchanging the x's and y's. This is the inverse relation. And then you solve both sides for y, or solve that equation for y, by taking the inverse sine or arc sine of both sides, which gets rid of the sine. And so your inverse function here would be sine inverse of x, or you can call it arc sine of x if you prefer. Let me go back here and define that to be our function f of x. So that inverse of f notation makes more sense. Okay, and one thing that happens when you find the inverse is not only do you interchange the x's and y's in the equation, you also interchange the domain and the range. So everything that was x, the domain, all the x values we're using from that original function, that becomes the range. Those x values become y values. And every y thing becomes an x thing. So the range that we decided, the domain that we decided to keep, negative pi over 2 to pi over 2, becomes this. The range of this function up here, negative 1 to 1, becomes our domain of the inverse. Okay? And that range statement is important, and so something that I will do to remind you of the range of the inverse trig functions is that's supposed to be a circle centered at the origin. Pardon the inability to make that look good. And we can use anything from negative pi over 2 to pi over 2. This is kind of like a unit circle. And these are the values you can use for inverse sine or arc sine of x for the range. So if I ask you what's the sine inverse of 1/2, the answer has to be an angle between negative pi over 2 and positive pi over 2. Right? So we're only getting answers there. Now the other thing, the other ramification of interchanging the x's and y's is that if I were to graph the inverse function, whereas before I labeled the x-axis by intervals of pi over 2, I'm not going to do that on the y-axis. And the y-axis was in terms of 1s, so I'm going to do that on the x-axis now, because that'll make it easier to graph. And for every point on the function that's graphed there, the 1-to-1 in red there, I'm going to interchange the x and y for each of those points. So for example, the first one on the left is at negative pi over 2, negative 1. So that's going to go to negative pi, 1, negative pi over 2. And 0, 0 goes to 0, 0. And pi over 2, 1 goes to 1 pi over 2. And the graph looks like this. And notice that its range is from negative pi over 2 is the low point down here to pi over 2 is the high point, which corresponds to that unit circle idea I wrote over there to the right. Okay. Now let's do cosine. Same idea. So I'll mark the x-axis by intervals of pi over 2 and the y-axis by marks that are 1 each. And the cosine of 0 is 1, so that's a high value. Then it goes middle, low, middle, high, etc. And over here, middle, low, middle. And so this is the cosine curve. Oops. A little bobble there. There we go. All right. And so that's obviously not one-to-one. It does not pass the horizontal line test. And so we're going to keep the entire range. Looking at that, make sure that we do exactly the same thing as we did up there. So the range we're keeping is from negative 1 to 1. And we have lots of different intervals possible, so we do want to keep that as close to 0 as we can. So that means that we could go from negative pi to 0 or from 0 to pi. And of course, with a negative choice, it's just as good as a positive choice. Our choice is going to be to keep the x's that are positive and go from 0 to pi. And again, that's to retain every value from 1 down through negative 1. Okay? So, the inverse, oh, I forgot to write f of x equals y equals cosine of x. And the inverse of that is x equals cosine of y. Taking inverse cosine of both sides, or arc cosine of both sides, you get y equals cosine inverse of x, otherwise known as f inverse of x equals cosine inverse of x. And since the range was negative 1 to 1 for the original function, that means that the inverse is going to have a domain of negative 1 to 1. And because the domain that we decided to keep went from 0 to 1, that means that the range will be from 0 to 1. 0 to pi, excuse me. I said 0 to 1, I meant 0 to pi. So, looking at the graph of inverse cosine, so we're going to mark the x-axis by 1s. Oops, I think I need a little bit more room up there. Actually, let me do this way instead. Let's back up and start over. Okay, give myself a little bit more space here. So this is the graph of the inverse function. Again, we're going to make the x scale by 1s because the y scale on the function was by 1s. And we're going to make the y scale by pi over 2 because that was the scale on the x-axis for the regular function. So this is going to be the graph of y equals cosine inverse of x, also known as arc cosine of x. So using the points that I see, 0, 1 will go to 1, 0, switching the x and y pair. Pi over 2, 0 will go to 0, pi over 2. And pi, negative 1 will go to negative 1 pi. And that graph looks like this. Okay. Now, as a memory aid, as I did before, if we think of a unit circle, for cosine inverse, we can only use range answers that are from 0 to pi. That's it. Okay. Okay. So the other graphs are similar to that, and you can go back to a pre-cal textbook and look up what the inverse graphs look like and what the restrictions are. But let me just tell you, kind of as a summary of what you should get when you do this, is the reciprocal function of sine is cosecant, and it just so happens that cosecant inverse has basically the same restriction from negative pi over 2 to pi over 2, as does tangent inverse. And again, the way I remember some things is some little stupid trick that I learned when I first did this was I thought of tangent as a function that's dominated by sine, because it's sine of x over cosine of x. And so it has the same restriction basically that sine does, negative pi over 2 to pi over 2 essentially. Where those graphs have vertical asymptotes for the original graphs, of course those are things left out of this range, and so you should again look at the pre-calculus material again to make sure that you understand all of this. Okay, so that means that the other three, cosine inverse, secant inverse, and cotangent inverse, all basically have the restriction 0 to pi. Again, the vertical asymptotes in the original graph are left out of those points, but that's basically what the restrictions would be. All right, so if you look under at the next slide, you can see all of those domains and ranges spelled out. And if you look at the range, notice that negative pi over 2 to pi over 2 is a common thing for sine, arcsine, arctangent, and for arc cosecant, with maybe something left out. Like for the tangent, you can't use negative pi over 2 or pi over 2 because it has vertical asymptotes for the original graph at those x values. And cosecant, the graph of cosecant itself has a vertical asymptote at x equals 0. So that means 0 is left out of the range for arc cosecant. All right, so then if you turn to the next page, you'll see the graphs, the first two of which we did together, and the others hopefully explainable because you know what the graphs of the original functions look like. And given the restrictions that I've outlined, those are the graphs that you would get. Okay, so let's work a few problems here. A, what is arcsine of negative 1/2? I just don't like arc because it's more writing, so I'll always use sine inverse, but that's okay. Now, one thing you ought to realize is that the output of an inverse trig function, look at your y-axis, that's by pi over 2. And so it's an angle in radians. And so I always, when I'm asked to find a trig inverse value, I'm going to say, well, that's equal to some angle, which I'm going to call theta. Then I'm going to rewrite that equation according to what it means. Sine inverse of negative 1/2 equals theta means if you were to take the sine of some angle theta, the answer it should be -1/2. And so what I'm going to think about that, if I don't just have that one memorized, is I remember that sine of theta is defined to be y/r. And I know that that can happen at two places. One of those is here, where this is -1 and that's 2. Or the other place is over here, where this is -1 and that's 2. And in both cases, the reference angle, since that's a 30, 60, 90 right triangle, that reference angle is pi/6 in size. So, thinking about sine inverse, remember that was the one that only had answers from -pi/2 to +pi/2. So the only triangle that falls in there is the one on the right, the one that's in the fourth quadrant. But be careful, it's not a fourth quadrant like between 3pi/2 and 2pi. It's somewhere between -pi/2 and 0, if it's fourth quadrant here. So what angle is that? Well, that angle is -pi/6. -pi/6. Because we're going to go this way, clockwise, pi/6 to get to that place, to that ray. That is the terminal side of that angle. Okay, so we ignore the other one because it's not in the range of inverse sine. Let's do another one. B, arc cosine of 0. Inverse cosine of 0. Again, that's equal to theta, which means that the cosine of some angle theta is 0. Cosine is x/r. The only way a fraction can be equal to 0 is if the numerator is equal to 0. And so that actually happens at two places, that cosine is 0. It's equal to 0 here and here. And so it's either pi/2 or 3pi/2 or -pi/2 or something like that. But keep in mind, the only answer that's acceptable is the answer that's between 0 and pi. And of course, that's the one that is pi/2. So theta is pi/2. That's the only acceptable answer. Okay, C, arctangent of square root of 3. That's equal to some angle theta. And of course, that equation means that the tangent of some angle theta gives me square root of 3, which I'm going to write as square root of 3/1. So it's a fraction, because I know tangent is defined to be y/x. And so I'm looking for places where y is, let's say, square root of 3 when x is 1. That's one possibility. The other possibility is if x is -1 and y is -square root of 3. That also would give me a positive answer, y/x. And thinking about the range of tangent inverse, like sine inverse, it goes from -pi/2 to pi/2. So it's the first quadrant answer. That is a 30, 60, 90 right triangle where the reference angle here happens to be the 60-degree angle, so pi/3. And because that is the first quadrant answer that we want, that means that theta here is pi/3. Part D, arcsine of 0.3. Equals some number theta, which means that the sine of theta is 0.3, which I'm going to write as 3/10. So get an answer of 3/10. That could happen because, oh, sorry, I forgot to write the definition. Because sine of theta is y over r. That could happen here, where this is 3 and that's 10. Or it could happen here, where that's 3 and that's 10. This is not an angle that I'm familiar with because it's not a 30, 60, 90 right triangle. It's also not a 45, 45, 90 right triangle. So I don't know what that is from trig. So this particular one, because it doesn't have a triangle that comes out to be one of our special right triangles, is not an angle that we're going to find exactly. We're going to have to use our calculator. So as it turns out, if you type that in your calculator, make sure you're in radian mode, because all these answers will be in radians. You should get about 0.305, which is what that angle is right there in the first quadrant. Because again, and your calculator knows these things. It knows that the answer has to be between negative pi over 2 and pi over 2 for inverse sine. It's going to give you the correct answer if you use your calculator. Okay, now let's do a couple more of these. These are calculator active problems, and I want you to find arc cotangent of negative 34. Well, if you notice, there's no cotangent button, so there's no cotangent inverse button on your calculator. So I'm going to suggest that you set up this equation like we've been doing. Write that equation without the inverse part. So that means cotangent of theta is negative 34. But then instead of thinking the definition, because this is a calculator active problem and there is no cotangent inverse button, I'm not even going to draw a picture over there to the right. I'm going to try to rewrite this problem in terms of something that is on the calculator. Cotangent of theta is the same thing as 1 over tangent theta. So now we're getting into the realm of, oh, I know this button on my calculator. I'm going to take the reciprocal of both sides of the equation. So that means tangent of theta will be negative 1/34. Then to get theta, I'll do inverse tangent of both sides. And I want you to notice what happened there. The tangent inverse is not the reciprocal of arc cotangent. That's not what you're taking the reciprocal of. Notice, if you equate these two things, this thing and this thing, it's not the reciprocal of the function, it's the reciprocal of the argument. And that's very important to know. All right, so we type that in our calculator, and we get negative 0.029. And then we think about that for just a second. I hope you think about it. I said I wasn't going to draw a picture, but I think I will after all. Since tangent is y over x, that would mean that either y is negative 1. Oops, sorry. Y is negative 1. Oh, that was right. Y is negative 1 when x is 34. Or it's y that's positive 1 and x is negative 34. Okay. Now, since the original problem is arc cotangent, you need to realize that means that the answer has to be between 0 and pi. So the answer we're looking for, the correct answer for this, is the angle that goes from here to there. Bigger than pi over 2. In fact, it's almost pi. Well, almost pi and negative 0.029 don't seem like they're the same thing. This is a problem with cotangent and tangent. Tangent inverse on the calculator will always give you an answer that's between negative pi over 2 and pi over 2. But we're supposed to find arc cotangent of a number, and that has to be an answer between 0 and pi. So consequently, to make this work out, I hope you realize that this answer, negative 0.029, is collinear. So if you extend this ray out and this ray out, that's a line. And you can tell that because this reference angle and this reference angle are congruent, which means the only way that can happen is if those are vertical angles, which means the x-axis and those two rays have to form two lines that intersect at the origin. So how do you get from an answer halfway around the circle? Well, you add pi. So you are going to have to draw pictures and think about it, especially when it's cotangent inverse, because you might not get the answer you're actually supposed to get. This is supposed to be an answer between 0 and pi. So if you'll add negative 0.029, the answer that's in your calculator, add to that pi, you'll get 3.112 approximately. And of course, that's about the size of that red angle that's indicated in my picture. Let's do another one. Cosecant inverse of 5. Well, there is no cosecant inverse button. So from what we just discovered, it's not the reciprocal of sine inverse. It's sine inverse of the reciprocal of the argument. And you type that in your calculator, and you should get 0.201. So what would secant inverse, or arcsecant, of negative 3.4 be? Well, the reciprocal function for secant is cosine, so it's cosine inverse of the reciprocal of the argument, and you should get 1.869. Oops, wrote the wrong thing there. 869. Now the good news about these two, cosecant inverse and secant inverse, is they have the exact same ranges as sine inverse and cosine inverse have. So there's not a danger here that you'll get an answer that's not in the correct quadrant. They will be in the correct quadrants for these if you use your calculator. It's the tangent and cotangent, because they have different ranges that you have to think about it a little bit harder to get those correct answers. Okay, one of the things about inverses is that the composition of a function and its inverse gives you back what you started with, just like the composition of the inverse with the function gives you back x. A simple way of thinking about this is if your function is to add 2, the inverse of that is subtract 2. So if I said, think of a number, and you thought of 12, and I said, okay, I want you to subtract 2, 10. Now add 2, 12. You got back what you started with, right? Or if I asked you to add first and then subtract, so 12, add 2, 14, minus 2, 12. You get back to where you started. So those are true statements, but you do have to think about the restricted domains for these. Particularly this one right here, when you're trying to find f inverse, like arc cosine of something, that answer x has to be a valid angle for inverse cosine. It can't be out of the 0 to pi range. So that's something to be careful about. As an example, sine inverse of sine of pi. Well, we know that the sine of pi is 0, right? And sine inverse of 0 is equal to some number theta, such that the sine of theta is 0. And we know that that happens at two places on the circle. Sine is equal to 0 here and here. And which one of those is between negative pi over 2 and positive pi over 2? Well, obviously, that's 0, right? So that's equal to 0, not pi. We started with pi and didn't get pi back because sine inverse cannot have an answer of pi. So be very careful about that your ranges are considered when you have that kind of problem. So on the next page, you'll see some restrictions on x and y. If you have the composition like sine of arcsine of x, you always get back x. If x is between negative 1 and 1, of course. And arcsine of sine of y, going the other direction, always give you back y, where y is a number between negative pi over 2 and pi over 2. It's kind of what we were just saying. So you can read those others and make sure that you understand that those domains and ranges have to be maintained to get answers that you would hope to get. All right, so let's do a problem where we have to do this. So let's start with tangent inverse. They wrote arctangent. Tangent inverse of 2x minus 3 equals pi over 4. So what we're going to do is we're going to take the tangent on both sides of this equation. And for arctangent, if you look up there, tangent of arctangent of x is x. And notice there's no restriction above that for x, so x can be any real number. So tangent of tangent inverse of whatever will always be that whatever. You don't have to worry about that one. And tangent of pi over 4, of course, is 1. And so you solve for x by adding 3 and dividing by 2, and you get x equals 2. Okay. So now let's talk a little bit about calculus. That was all pre-calculus review. Let's get to some calculus now. We know that the derivative of the ln of x, a transcendental function, ln of x, is an algebraic answer 1 over x. And as we're about to see, the derivatives of the inverse trig functions are also algebraic, even though the inverse trig functions themselves are transcendental. So let's start with y equals sine of x. And find its inverse by switching the x's and y's. And instead of solving for y, we're looking for the derivative of that equation I just wrote in pink, because that is the inverse equation. So what I want to do is I want to use implicit differentiation and take the derivative on both sides of that equation with respect to x. Now, everything in pink right now is the inverse equation because the x's and y's have been switched. So when we find dy dx for this, it will be dy dx for arcsine. Okay, that's what we're headed. Okay. So keep in mind that if we solve this for y, we would get sine inverse of x, as we did above. So the derivative of x with respect to x is 1. The derivative of the sine of something is the cosine of that something times the derivative of that something because of the chain rule. Now to solve for dy dx, you could divide both sides by cosine y to get dy dx by itself. Now typically we want our derivatives to be in terms of x if we're taking the derivative with respect to x. So this 1 over cosine y, although not incorrect, is not where I want to stop. So I want to get rid of that cosine of y. Okay? So let's think about this. If x is sine of y, let me draw a little picture here to help us think about what's going on here. If I have a right triangle and we're taking the sine of y, which means the angle is y, and the answer is x, well, x over 1, right? So what I'm using here is the fact that sine of y is equal to x, which I'm going to call x over 1. And we know that sine is opposite over hypotenuse. And I'm kind of curious about what the third side is. And since it's a right triangle, I know that the Pythagorean theorem holds that leg squared plus leg squared equals the square of the hypotenuse. So using subtraction, I can get question mark squared by itself. And then to solve for question mark, I can take the square root of both sides. And then I'm going to think, okay, well, big deal. Oh, yeah. Look what we were trying to do. Kind of focus back in on what we were trying to do. I want to get rid of cosine y. And so I need to know what cosine of y is equal to, where y is defined as above and all this trig stuff that I've written over here. So cosine is adjacent over hypotenuse. So that's going to be square root of 1 minus x squared over 1, which is just that radical. And so what that means is, by substitution, I can take the cosine of y out and write this in its place. And of course, that's an algebraic expression. So the derivative of, let me draw a conclusion here. The derivative with respect to x of arc sine of x, or inverse sine of x, is therefore 1 over the square root of 1 minus x squared. Okay? Probably ought to write that a little bit more clearly. That doesn't look like a square. Tried to write it too small, I think. There we go. Now it looks like a square. Okay. So if you turn to the next page, if we've done a similar thing for the other 5 inverse trig functions, by starting with the regular function and forming the inverse by switching x and y, and then using implicit differentiation to find dy dx, and then use a triangle to rewrite that in terms of x as your final answer. Those are the results. So look at those answers. Notice that the derivative of arc sine and the derivative of arc cosine are very similar. The only difference is that the arc cosine's derivative is the opposite of arc sine. And the same thing happens for tangent and cotangent inverses. The only difference is a negative sign. Likewise for secant and arc secant and arc cosecant. So those are the algebraic expressions for the derivatives of the inverse trig functions, and those are ones that you should know, therefore you need to commit them to memory. So I'm going to stop this recording now and go to the next one before we go to example 4. I wanted to go to this new page, our new recording, so that I'm not going to run out of room on this one. So go ahead and go to the next recording. This is the end of that first part.